Andromeda is much larger than most people realise. When we hear the name, we imagine a distant smudge in the sky or a photograph from a telescope. But Andromeda is not just a small blur hanging beyond our vision. It is a massive, spiral galaxy, the closest large neighbour to the Milky Way, and one of the largest structures visible to the naked eye. It looks tiny only because of the incredible distance separating us from it. In reality, Andromeda is a giant stretching across the night sky in a way that few people ever understand. If our eyes were sensitive enough, the Andromeda galaxy would appear 6 times wider than the full moon. It is already there, spanning a huge portion of the darkness above us. But our eyes cannot detect the faint light that spreads across that width. This is the first hint that Andromeda is not a simple object. It is enormous, and the space between us and Andromeda is even more enormous. The galaxy sits about 2.5 million light-years away. That distance alone is almost impossible to imagine. A light-year is already a huge measurement. The distance light travels in 1 year while moving at nearly 300,000 kilometers every second. Multiply that by millions, and the space between the Milky Way and Andromeda becomes a gulf greater than anything we experience in our everyday lives. And yet, despite this distance, Andromeda is close by galactic standards. Space is so large that even millions of light-years count as neighbours. Standing on Earth and looking at Andromeda, it feels small because we are overwhelmed by the emptiness in between. Our galaxy and Andromeda are separated by a vast void called intergalactic space. This region is not packed with stars or filled with glowing matter. It is mostly empty, with only thin clouds of gas and a few wandering stars drifting alone. It is a silent, dark stretch of cosmic nothingness, and Andromeda's faint light must cross all of it to reach us. That faintness hides its true size. If you could remove the distance and bring Andromeda closer, the galaxy would tower across our sky like a glowing storm of stars. But Andromeda is not only large, it is massive. It contains around 1 trillion stars, far more than the Milky Way. Each of these stars is a sun in its own right. Some are larger than our sun, some are smaller, some are young, and some are ancient. Each star may have planets. Some may have moons or rings or debris. Some may host habitable worlds. Throughout Andromeda, entire solar systems orbit peacefully within spiral arms that stretch for tens of thousands of light years. When we talk about Andromeda, we're not talking about one object. We are talking about an entire universe of stars, planets, nebulae, and cosmic structures bound together by gravity. The shape of Andromeda also adds to its scale. It is a spiral galaxy like the Milky Way, with wide arms that curl outward and a bright central bulge. These arms are filled with gas clouds where new stars form. The central region contains older stars and possibly a supermassive black hole with millions of times the mass of the Sun. The entire galaxy rotates slowly, completing one full turn over hundreds of millions of years. Everything inside it, stars, dust, planets, black holes, moves together like a giant cosmic wheel. This rotation is not chaotic, it is guided by gravity, which shapes Andromeda's form and holds everything in place. The width of Andromeda is staggering. From one edge to the other, it stretches more than 220,000 light years. That is more than twice the width of the Milky Way. If the Milky Way and Andromeda were placed side by side, Andromeda would noticeably dominate the view. But even this comparison does not fully show how large it is. When we talk about hundreds of thousands of light years, we are dealing with distances that light itself requires centuries to cross. If you could travel at the speed of light, you would still need 2 lifetimes to get from one side of Andromeda to the other. Inside that enormous span exists every possible stage of stellar evolution. There are young bright stars lighting up the spiral arms. There are aging red giants drifting into the ends of their lives. There are regions where stars explode as supernova, releasing intense energy and reshaping surrounding space. There are dense clusters where stars are packed more tightly than anything near our Sun. There are quiet, stable systems where planets form and drift for billions of years. Andromeda contains the entire story of stellar life, repeated countless times across its vast expanse. What makes the scale of Andromeda even more striking is that it does not sit alone. It is the largest galaxy in our local group, a small cluster of galaxies that also includes the Milky Way, the Triangulum galaxy, and dozens of dwarf galaxies. But Andromeda is the giant among them. Its gravitational influence extends far beyond its visible structure. It controls the motion of nearby dwarf galaxies. It shapes the local group structure. It interacts subtly with the Milky Way across the void. This interaction is slow and delicate now, but it will not remain that way. Andromeda is moving toward the Milky Way at about 110 kilometers per second. To us, that speed feels unimaginable, but across cosmic distances, it is steady and gentle. Over billions of years, this motion will bring the two galaxies together. Their shapes will distort, their stars will shift, their gas clouds will collide. Ultimately, the two galaxies will merge into a single, larger galaxy, sometimes called Milkomeda. This future collision is one of the biggest events in the local group, and Andromeda's massive scale is at the center of it. Even though this collision is billions of years away, we already see the gravitational dance beginning. Subtle distortions in both galaxies' motions show that they are responding to each other. Both galaxies are being pulled slightly. Both galaxies are adjusting their shapes. This slow-motion interaction is a reminder that gravity binds everything in the universe, regardless of the space between them. And this is only the beginning of understanding Andromeda's scale. Its stars, its mass, its motion, its influence, all of it reveals a galaxy far larger and more complex than the faint blur we see in the sky. The true scale of Andromeda becomes even clearer when we look at its halo, a vast invisible sphere of dark matter surrounding the galaxy. This halo stretches far beyond the visible spiral arms. It may extend more than 1 million light-years from the center of the galaxy. This means Andromeda's gravitational influence reaches distances almost half of the gap between us. Most people imagine Andromeda as a flat disk, but the galaxy is actually surrounded by a massive three-dimensional envelope of dark matter that shapes its structure, its rotation, and the movement of galaxies around it. This halo contains far more mass than the stars we see. Without it, Andromeda's fast rotation would tear it apart. The dark matter binds the galaxy with a gravity we cannot see, but can measure through the motion of stars. Inside this halo, Andromeda continues to pull in smaller galaxies. Many of its dwarf companions orbit in long looping paths. Some are being torn apart by Andromeda's gravity. Streams of stars, remnants of swallowed galaxies, stretch through the halo. These star streams reveal Andromeda's violent past. Over billions of years, Andromeda has consumed other galaxies, growing larger each time. What we see today is not a quietly formed structure. It is the product of endless mergers, collisions, and gravitational interactions. Every star stream is a signature of this history. Every distortion in the halo is a memory of something Andromeda devoured long ago. Our Milky Way has undergone a similar history, but Andromeda's is more dramatic. Its sheer size means it has consumed more galaxies, absorbed more stars, and built itself into a giant. The galaxy we observe today is a survivor of cosmic evolution. Its spiral arms are shaped by these interactions. Its central bulge is built from older stars left behind after earlier collisions. Even its future collision with the Milky Way will add to this ongoing story. The universe writes the biography of galaxies through gravity, and Andromeda's biography is written across millions of light years. One of the most remarkable things about Andromeda's scale is how it appears from Earth. To the naked eye, it looks like a tiny, faint patch of light. To a long exposure camera, it becomes a detailed spiral galaxy. But if the human eye were more sensitive, Andromeda would fill a huge section of the night sky, larger than many constellations. It is already above us, dominating our sky, but our eyes cannot detect most of its light. The galaxy's light is faint, not because it is small, but because it is far. Its true width, hundreds of thousands of all light years, all she always is lost behind the sheer distance separating us. If Andromeda were suddenly moved 10 times closer, it would stretch across the sky in a dazzling view. Its spiral arms would shine like great ribbons of stars. Its bright core would glow like a celestial torch. The night sky would no longer be dark. The galaxy would become a permanent presence, changing the appearance of the heavens forever. But even now, in its distant position, Andromeda is still the largest single object visible without a telescope. This alone reveals its enormous size. The distance between the Milky Way and Andromeda, 2.5 million light-years, also carries a deeper meaning. It tells us how isolated galaxies truly are. Even though they form groups and clusters, the space between them is vast. Light from Andromeda has taken millions of years to reach us. When we look at Andromeda, we're not seeing it as it is today. We're seeing it as it was before early humans even existed. Every galaxy photograph is a time capsule, and Andromeda's image is older than our species. This distance also gives us insight into motion on cosmic scales. Andromeda is moving toward us faster than most galaxies in the universe. Because of cosmic expansion, almost all galaxies are moving away from the Milky Way. But within the local group, gravity is stronger than expansion. Andromeda's approach shows that gravity binds our region of the universe together. Even across millions of light years, the pull is strong enough to overcome the expansion of space. This pull will eventually lead to collision. When the Milky Way and Andromeda collide, the event will not be violent in the way we imagine collisions. Stars will not crash into each other because space between stars is enormous. Instead, the gravitational shapes of the two galaxies will merge and distort. Spiral arms will stretch and twist. Stars will be thrown into new orbits. The central regions may ignite bursts of star formation. The galaxies will pass through each other, separate, and then fall back together. This dance will continue until they settle into a new shape, likely a massive elliptical galaxy. In that future galaxy, many stars from Andromeda and the Milky Way will orbit peacefully together. Our Sun, if it still exists, will follow a new path. But long before the merger finishes, Andromeda will dominate Earth's sky. It will stretch across the heavens as a dramatic, glowing arc. No human will be alive to witness it, but the view would be breathtaking, a reminder of the true scale of galaxies and the motion of the universe. When we talk about Andromeda's scale, we are not only describing its size, we are describing its role in cosmic evolution. It is a galaxy large enough to change the shape of the local group. It is a galaxy bright enough to be seen across millions of light years. It is a galaxy massive enough to influence the Milky Way's future. And it is a galaxy old enough to carry fragments of countless past galaxies within its halo. Every part of Andromeda, from its core to its spiral arms to its extended halo, reveals a structure far more enormous than our senses can perceive. Its presence in the night sky is a soft whisper of something incredibly large. The faint patch we see is just the centre. The rest of the galaxy extends across an area we never notice, and beyond what we can see, its halo stretches even farther, shaping the darkness with invisible gravity. Understanding the true scale of Andromeda means understanding how galaxies grow, how they interact, and how they shape the future of their cosmic neighbourhoods. It means realising that the universe is not only vast but structured in ways deeper than we ever imagined. Andromeda is not just our neighbour, it is a giant waiting on the other side of a dark ocean of space. And one day, our galaxies will become one. Andromeda looks simple from far away, but when you begin to examine its structure, layer by layer, its scale becomes almost impossible to grasp. The galaxy is not just a flat disk, it is a three-dimensional system with depth, height and thickness, stretching tens of thousands of light years in every direction. Most people imagine galaxies as thin spirals, but Andromeda has volume. Its disk alone is several thousand light years thick, filled with stars, dust, gas, nebulae, and clusters that are constantly moving, colliding, and evolving. If you could stand inside Andromeda and look across it, the galaxy would not look like a flat picture. It would feel like being inside a vast, glowing city of stars, extending in every direction. The central region of Andromeda is especially large. It contains a dense bulge of older stars that crowd closely together near the supermassive black hole in the core. This bulge spans tens of thousands of light years. It is not an isolated sphere. It flows smoothly into the spiral arms and connects to the rest of the disk. The stars near the centre orbit rapidly, pulled by the strong gravitational influence of the dense mass collected there. If you were close to this central region, you would see stars screaming past at tremendous speeds, moving hundreds of kilometers per second, rushing around the black hole with immense momentum. This motion is a direct sign of the galaxy's mass. Nothing moves that fast unless gravity is extremely powerful. Beyond the central bulge, Andromeda's spiral arms reveal even more scale. These arms are not thin, delicate structures. They are massive, thick ribbons containing hundreds of billions of stars. Each arm stretches tens of thousands of light years from the core, curving gently through the galaxy. They are filled with star-forming regions, clouds of gas collapsing under gravity to create new stars. Some regions glow with bright blue light from young, hot stars. Others glow faintly with reddish light from older stars. These colour variations show us how Andromeda has been forming stars across billions of years. It is not a static structure. It is alive with motion, growth, collapse, and rebirth. The spiral arms also contain enormous star clusters. Some are loose groups of dozens of stars. Others are globular clusters, dense spherical balls containing hundreds of thousands of stars packed into a small region. Andromeda has more than 450 globular clusters, more than twice the number found in the Milky Way. Each cluster is a miniature galaxy orbiting the larger one. Some are so old that they formed shortly after the universe began. These clusters act like fossils, showing us what Andromeda's earliest stars were like. They orbit in long, sweeping paths that take them far above and below the galactic disk. Even these orbits reveal Andromeda's enormous gravitational pull. In addition to its stars, Andromeda contains vast clouds of hydrogen gas stretching across its entire disk. These clouds provide the raw material for future generations of stars. They're cold, quiet, and dark until something disturbs them. Another cloud passing nearby, a shock wave from a supernova, or the spiral arms themselves pushing the gas together. Once disturbed, the gas collapses and heats up, forming new stars. This cycle of collapse and birth has been happening in Andromeda for billions of years and will continue long after our own sun has burned out. Andromeda also has immense dust lanes weaving through the arms. These dark, thick regions absorb starlight, creating beautiful patterns of shadow across the galaxy. The dust is made of tiny particles, carbon, silicates, and metals released by dying stars. These particles eventually become part of new stars, planets, and even the building blocks of life. Dust is essential to the galaxy's evolution, and Andromeda contains staggering amounts of it. If you travelled through the galaxy, you would pass through these dusty regions, moving through clouds so vast they would take light years to cross. When we zoom out and look at the entire galaxy, its rotation adds another layer to its scale. Andromeda rotates roughly once every 250 million years. This means that if you lived long enough to watch a full rotation, you would see the galaxy slowly turning like a cosmic wheel. The stars follow specific paths determined by the galaxy's mass and the distribution of dark matter in the halo. Without dark matter, Andromeda's outer regions would spin far slower. Instead, they move quickly, showing us that most of the galaxy's mass is hidden. Even more surprising is the way Andromeda interacts with nearby galaxies. It is not isolated. It has several dwarf galaxies orbiting it, many of them stretched and distorted by its gravity. Some of these dwarf galaxies are being pulled apart, leaving behind trails of stars. Others orbit in synchronized patterns, creating a system far more complex than a single galaxy drifting through space. Andromeda is like a gravitational giant surrounded by smaller companions, each one moving along paths shaped by Andromeda's massive halo. This entire structure, the disk, the bulge, the spiral arms, the halo, the clusters, the dwarf galaxies, moves through space at tremendous speeds. Andromeda is not stationary. It travels through space just like the Milky Way. The two galaxies move toward each other, pulled together across immense distances. The speed of this motion tells us how powerful Andromeda's gravity truly is. Only a massive object can influence another galaxy across millions of light years. Even the light we see from Andromeda is shaped by its scale. Because the galaxy is so large, light from the core reaches us sooner than light from the outer edges. When we look at Andromeda, we are looking at different regions from different moments in time. The full galaxy is a blend of information arriving across thousands of years. Our view is always slightly uneven, stretched across time as well as space. Andromeda is not simply big. It is layered, structured, dynamic, and alive. Its true scale is revealed not just by its width, but by every motion, every star, every orbit, and every cloud within it. The galaxy's patterns reflect billions of years of evolution. Its present appearance is the result of countless interactions, mergers, and collapses. Each part contributes to the sense of overwhelming vastness. The further we explore Andromeda, the more we realize how much of its true size is hidden from simple observation. Its visible stars represent only a fraction of its full structure. Much of its mass lies in regions we cannot see. The halo extends so far beyond the visible disk that, if you could somehow outline its true boundary in the night sky, Andromeda would appear as a giant sphere dominating the constellations. The faint glow we see today is only the bright inner region. Everything else stretches outward into darkness, merging quietly with intergalactic space. This halo is not just large, it is dense with history. As Andromeda absorbed smaller galaxies over billions of years, it left behind streams of stars that orbit far from the central disk. These streams are scattered across the halo like ribbons, some so long that they stretch tens of thousands of light years. Each one represents a galaxy that no longer exists. These remnants reveal how Andromeda grew into a giant. The galaxy we observe today is the result of cosmic cannibalism, of countless mergers that increased its mass and reshaped its form. Many of these remnants still orbit Andromeda, subtle enough that telescopes only recently detected them. Some dwarf galaxies have already merged completely, their stars blending into Andromeda's outer regions. Others remain intact for now, but stretched, their shapes elongated by tidal forces. These distorted dwarfs show how powerful Andromeda's gravity is even far from the disk. Its halo not only influences these galaxies, it reshapes them. This gravitational dominance is not one-directional. Andromeda is so massive that it affects the Milky Way even across millions of light years. Small distortions in our galaxy's motion reveal this. The Milky Way is being pulled slightly off-center by Andromeda's gravity. Our entire spiral structure is moving slowly toward that distant giant. Even though space between the two galaxies is mostly empty, gravity connects them. This connection stretches across the void and shapes the future of both systems. If we could view Andromeda from a distance outside the local group, the galaxy would look like a glowing wheel surrounded by smaller companions. Its spiral arms would appear symmetrical from afar, with clumps of bright blue where young stars cluster together. The faint haze of older stars would fill the space between the arms. The core would shine intensely, brighter than anything in our sky. All around the disk, tiny specks, dwarf galaxies, would orbit in slow, skewed paths, and beyond them, the halo would extend into darkness, invisible but gravitationally dominant. Within Andromeda, star formation varies dramatically, depending on location. The inner arms contain dense clouds of gas that collapse frequently, giving birth to young, luminous stars. These regions glow in bright blue light, revealing active stellar nurseries. In contrast, the outer regions of the disk are quieter, with fewer gas clouds and older stars. These areas glow softly, with red and yellow light, older populations that have burned steadily for billions of years. This distribution of colours shows us Andromeda's age structure, its history written in light. And then there is the central black hole. It is millions of times the mass of the Sun, anchoring the galaxy's core. Stars near the centre orbit incredibly quickly, completing full rotations in far less time than stars in the outer disk. These speeds give us precise measurements of the galaxy's mass. The black hole itself is invisible, but the motion around it makes its presence unmistakable. The centre of Andromeda is one of the most extreme environments in the local group, filled with intense radiation, tightly packed stars, and the gravitational influence of the supermassive black hole. But despite this extreme core, the rest of the galaxy is surprisingly peaceful. Most regions are stable, with stars drifting quietly along their orbits, barely interacting with anything else. The average distance between stars in Andromeda is so large that collisions are rare. Even during the future merger with the Milky Way, direct star collisions will be extremely unlikely. The galaxy is massive, but it is mostly empty space, an ocean of stars spread across hundreds of thousands of light years. This emptiness is what makes the galaxy appear faint from Earth. If the stars were packed closely together, Andromeda would shine brightly in the night sky. Instead, the light spreads thinly across the disk. The glow we see is the combined light of billions of stars, diluted by vast distances. That faintness hides its true size. Humans see only the bright central core without realizing the rest of the galaxy frames half the region around it. Imagine if your eyes could detect faint light as well as a modern telescope. Andromeda would no longer appear as a small smudge. It would fill a huge arc of sky. You would see its arms stretching outward, the dust lanes cutting through them, and the faint glow of star clouds drifting far from the centre. The sky would contain a second galaxy beside the stars of the Milky Way. Only the limit of human vision prevents us from seeing the true scale of what hangs above us. The distance that hides Andromeda's size also hides its motion. Light from Andromeda takes 2.5 million years to reach us. This means everything we see today happened long before humans existed. The galaxy has moved since then. Stars have completed portions of their orbits. The spiral arms have shifted. The galaxy has rotated slightly. Even the path of Andromeda toward the Milky Way has changed. We observe an ancient snapshot of a dynamic system. This time difference expands dramatically when we consider that Andromeda is not a static structure. Stars are constantly being born and dying. Supernovae explode, gas clouds collapse, black holes absorb matter. Entire clusters shift positions. The galaxy we see today is not exactly the galaxy that exists right now. This distance temporal gap adds another layer to Andromeda's scale. It is not simply large in space, but large in time. Its light carries the history of billions of years, stretching across cosmic distances like a record of the universe's long memory. Every observation, every measurement, every detection reveals one conclusion. Andromeda is far larger, more massive, more complex, and more influential than the faint patch of light suggests. It is a galaxy shaped by gravity, history, and time. Its true scale goes far beyond its visible form. It reaches into the darkness, extends across the local group, and connects to the Milky Way in an invisible, gravitational embrace. Understanding Andromeda's true scale means we must expand our sense of distance, time, motion, and perspective. It requires us to see beyond what our eyes can detect and imagine the vast structures hidden behind faint light. Andromeda is a reminder that the universe is not made of what we easily see. It is made of enormous systems that reveal themselves only when we look deeper. The true scale of Andromeda becomes even more astonishing when we explore how it moves not only through space but through time. Galaxies are not fixed objects hanging quietly in the sky. They drift, rotate, evolve, and collide over billions of years. Andromeda is no exception. It travels through the universe with incredible momentum, carrying its stars, planets, and dark matter halo like a massive cosmic ship crossing a silent ocean. Every part of Andromeda, its disk, its halo, its black hole, its dwarf galaxies, moves together in a coordinated ballet, shaped entirely by gravity. This motion is slow from our perspective, but enormous in scale. When you measure it across millions of years, Andromeda becomes a dynamic, constantly changing structure. Right now, Andromeda is moving toward the Milky Way at about 110 kilometers per second. That speed is far faster than anything we experience in daily life. But because of the immense distance between us, that motion feels almost frozen. It will take billions of years before the galaxies meet. Still, this approach is one of the clearest signs of Andromeda's scale. A galaxy does not move toward another galaxy unless its mass is enormous. The gravitational pull required to draw two massive spirals together across 2.5 million light-years must come from structures far larger and heavier than anything humans can imagine. Their future collision is not a violent crash, but a slow gravitational blending that will reshape both galaxies. But long before the collision actually begins, Andromeda's motion influences the Milky Way. Through the vast emptiness of intergalactic space, gravity pulls subtly on both galaxies. This pull affects their orbits around the center of the local group. Both galaxies fall slowly toward each other like two continents drifting across an ancient sea. Their halos are already overlapping. The outermost edges of both galaxies, invisible to the human eye, meet halfway across the void. These invisible boundaries show that galaxies are not isolated disks. They are enormous spheres of influence that stretch far beyond what we can see. The motion of Andromeda also reveals the structure of the dark matter halo surrounding it. The halo is not static. It moves with the galaxy, guiding the motion of stars and dwarf galaxies in its vicinity. It creates a gravitational field that extends deep into the local group. This means the shape of space around Andromeda is distorted long before you reach its visible disk. The motions of nearby objects tell us how this halo is arranged. Some dwarf galaxies orbit quickly, others slowly, depending on their distance from the center. Their paths trace the invisible structure of the halo, like marbles rolling across a magnetic field. The rotation of Andromeda's disk is another clue to its immense scale. Stars near the center rotate quickly because of the dense mass in the core. But surprisingly, stars in the outer disk rotate almost as fast, even though the visible matter thins out dramatically. This flat rotation curve is one of the strongest pieces of evidence for dark matter. Without an enormous hidden mass surrounding the galaxy, these outer stars would drift away. Instead, they remain bound. Their steady rotation shows that Andromeda's true mass is far greater than the light we see. Dark matter makes up the majority of the galaxy's mass, shaping its rotation and keeping it stable across hundreds of thousands of light years. This stability is remarkable given Andromeda's age. The galaxy is more than 10 billion years old. Over that time, it has undergone countless changes. It has merged with smaller galaxies, absorbed star clusters, formed new spiral arms, and reshaped its halo. It has experienced periods of intense star formation and periods of quiet evolution. Every one of these phases has left a signature in the galaxy's structure. The current shape of Andromeda is the product of these billions of years of motion, collisions, and gravitational reshaping. These signs of past interactions appear in many forms. Some are faint ripples in the halo. Others are long streams of stars arcing far from the disk. Some are asymmetries in the spiral arms, showing where gravity has pulled the structure unevenly. Others are remnants of dwarf galaxies caught in mid-merger, partially torn apart by Andromeda's gravity. Together, these features reveal a galaxy that has grown through cosmic cannibalism. Andromeda is not merely large because it formed that way. It is large because it has consumed dozens of smaller systems. The Milky Way has done the same, but Andromeda's past mergers appear more dramatic. This is one reason Andromeda is slightly more massive. Its disk is broader, its halo is thicker, its central region is denser. The galaxy is a giant not only in size but also in history. Every star, every cloud, every stream in its halo tells part of that history. Andromeda's true scale is not only in its physical dimensions, it is also in the vast span of time that shaped it. If we could watch Andromeda evolve in fast motion, compressing billions of years into minutes, the view would be breathtaking. You would see spiral arms twist and shift. You would see dwarf galaxies plunge into the halo, dissolving into streams. You would see bursts of star formation flare up in the arms. You would see the central region grow brighter as stars gather. You would see the entire galaxy rotate slowly, like a wheel turning through cosmic time. The idea that galaxies are static structures falls apart when you observe them across deep time. They are living systems, always changing, always in motion. This perspective also helps us understand the future. As Andromeda approaches the Milky Way, the initial signs of the merger will be subtle. The halos will overlap more deeply. The galaxies will distort slightly. Their spiral arms will begin to warp. Star formation may increase in certain regions as gas clouds collide. Over millions of years, the galaxies will draw closer and pass through each other. The stars will barely notice. The space between them is too vast, but their paths will shift dramatically. Some stars will be thrown into new orbits. Others will be ejected into intergalactic space. Some may fall toward the central black holes, causing bursts of intense radiation. Eventually, the two galaxies will merge into one. The new galaxy will likely be an enormous elliptical system. The neat spiral patterns will fade. The halos will blend. The central black holes will spiral together and merge, releasing powerful gravitational waves. This new galaxy will be far larger than either Andromeda or the Milky Way. It will dominate the local group, and its creation will be one of the most dramatic transformations in cosmic history. But even long before this happens, Andromeda's scale continues to influence the Milky Way. Its gravitational pull shapes the motion of our galaxy's outer halo. It affects the path of stars far beyond the disk. It determines how dwarf galaxies orbit the Milky Way. The local group is not a cluster of independent systems. It is a gravitational environment shaped by the interaction of two giants. Andromeda is one of those giants. Everything about Andromeda, its mass, its motion, its halo, its dwarf companions, its history, points to a scale far beyond our natural intuition. We see only the smallest fraction of what the galaxy truly is. The faint blur in the sky hides a structure so massive that it shapes the future of the Milky Way itself. And this is only the first half of the full story. The scale of Andromeda becomes even more striking when we examine how its gravity influences not just dwarf galaxies and star streams, but the entire structure of the local group. The local group contains more than 50 galaxies, but most of these are tiny dwarfs. Only two large spirals dominate the region, the Milky Way and Andromeda. These two galaxies form the gravitational centre of the local group, with every smaller galaxy orbiting around them in some way. Andromeda plays a leading role in this system. Its mass determines the motion of many dwarfs. Its halo reaches deep into the empty regions between galaxies. Its gravity helps shape the balance between the local group and the larger structures beyond it. When scientists measure the motion of galaxies far from Andromeda, they still see its influence. Even galaxies that lie closer to the Milky Way feel a subtle pull from Andromeda's enormous halo. It is so massive that it stretches the geometry of space across millions of light years. This is one of the clearest signs of its true scale. Even at distances where light takes millions of years to travel, Andromeda's gravity does not fade. It operates across unimaginable distances, gently guiding the dance of galaxies around it. This influence is not something we notice day to day, but on cosmic timescales, it determines everything. The connection between the Milky Way and Andromeda is a powerful example. Although space between them is mostly empty, their halos overlap. This means the two galaxies are already connected by a shared gravitational environment. Long before their disks touch, long before their spiral arms distort, they are already influencing each other. The region between them is not a dead void, but a dynamic space shaped by the gravity of two giants drifting toward an inevitable meeting. If you could see gravity the way you see light, the void between the Milky Way and Andromeda would not look empty. It would look stretched and curved, a landscape of invisible contours pulling both galaxies closer. The halos would appear like two giant bubbles touching in the middle, their shapes warping as the galaxies respond to each other. This invisible structure is far larger than either galaxy's disk and reveals how extensive Andromeda's influence really is. Beyond the local group, Andromeda participates in even larger motions. Our entire collection of galaxies is drifting toward another structure called the Virgo cluster, a massive gathering of thousands of galaxies. That, in turn, is falling toward an even more enormous region known as the Great Attractor. Every structure in the universe falls toward something larger. Gravity pulls everything into deeper wells of mass. Andromeda's motion toward the Milky Way is part of a chain reaction happening across the entire universe. Its scale cannot be understood in isolation. It is part of a network of motions that stretch billions of light years in every direction. Yet despite all of this large-scale motion, most of Andromeda remains calm. Stars orbit peacefully inside their massive galaxy. Gas clouds drift slowly into denser regions. New stars ignite in glowing blue clusters. Dust lanes shift gradually as the disk rotates. The galaxy is so large that even dramatic motions take millions of years to show noticeable change. From a human perspective, Andromeda seems frozen, but across cosmic time, it behaves like a living organism, constantly evolving. One of the most important measurements that reveals Andromeda's scale is the speed of stars inside it. The faster stars move, the more mass must be present. When astronomers measured these speeds, they discovered something surprising. Stars in the outer disk were moving far faster than expected. There is not enough visible matter to explain their motion. Something unseen must be providing the extra gravity. This invisible mass is dark matter, and most of Andromeda's mass comes from it. Without dark matter, Andromeda would not hold together. Its stars would escape into space, its halo would dissolve, its spiral arms would unravel. Dark matter fills Andromeda's halo like a ghostly foundation. It does not emit light, it does not absorb it. It does not interact with normal matter except through gravity, but its presence is undeniable. Dark matter tells us that Andromeda's true mass is far greater than what we see. The visible disk is only a small fraction of the whole galaxy. The halo contains far more mass than the stars. This hidden structure is enormous, extending hundreds of thousands of light years beyond the visible disk. When we talk about the true scale of Andromeda, we must include this invisible component. Without it, our picture of the galaxy would be incomplete. All of these layers, stars, gas, dust, dark matter, dwarf galaxies, stellar streams, combine into a structure of unbelievable size. But the most surprising thing about Andromeda is that it is not special. It is one of trillions of galaxies in the universe. Each of those galaxies has its own structure, its own history, its own halo, its own motion. Andromeda stands out only because it is close enough for us to study in detail. The vastness we see in Andromeda is repeated across the cosmos. Every galaxy is a giant, even the ones that appear small in telescopes. Andromeda's closeness makes it a window into the universe. It allows us to understand how galaxies form, evolve, and interact. It helps us study the role of dark matter. It shows us how mergers shape galaxies. It helps us understand how spiral structures form and dissolve. It gives us clues about our own past and our own future. When we study Andromeda, we are not just studying one galaxy. We are studying the nature of galaxies themselves. One important realization is that galaxies like Andromeda and the Milky Way are rare only in our perspective. In the full universe, they are common. The universe contains billions of galaxies as large as Andromeda or larger. Some are much more massive. Some contain hundreds of trillions of stars. Compared to the universe's largest structures, Andromeda is not even close to the top of the scale. Yet from our viewpoint, Andromeda feels unimaginably large. That contrast between our limited intuition and the immensity of the universe is what makes studying Andromeda so powerful. It forces us to expand our understanding of size and distance. Even the empty space between stars inside Andromeda reveals its scale. The average distance between stars is far greater than the distance between stars in our own region of the Milky Way. Andromeda contains vast star deserts, regions where stars are separated by light years of empty space. These regions show that galaxies are not solid structures. They are fragile, delicate collections of stars bound only by gravity. If you flew between the stars inside Andromeda, you would spend years travelling through darkness before seeing another star up close. The galaxy's brightness comes from its sheer number of stars, not from how densely they are packed. This emptiness is what allows galaxies to merge without destroying themselves. When Andromeda and the Milky Way collide, most stars will pass through each other without ever coming close. The galaxies will merge, but the stars will remain intact. This gentle collision happens because galaxies are mostly space. Andromeda appears dense in photographs, but that density is an illusion created by distance. Up close, the galaxy is sparse and spacious, with immense gaps between stars and even larger gaps between clusters. The final piece of Andromeda's scale comes from its age. The galaxy is older than any single star inside it. It began forming more than 10 billion years ago. Over that time, it has changed shape, merged with other systems, formed hundreds of billions of stars, and created structures that stretch across hundreds of thousands of light years. The Andromeda we see today is the result of ancient processes that began long before the Earth existed. Its age adds another dimension to its scale. It is large not just in space but in time. When we put all of this together, the mass, the halo, the rotation, the motion, the star streams, the dwarf galaxies, the history, the future collision, we see that Andromeda is not only one of the largest structures in the night sky, it is one of the most impressive structures we can study closely. Its scale challenges our imagination. Its influence shapes our region of the universe. Its future is tied to ours, and its presence in the night sky is a constant reminder that the universe is far larger and more complex than it appears. The true scale of Andromeda becomes even clearer when we trace how its stars are arranged across its enormous disk. The distribution of stars inside Andromeda is not random. It forms patterns that stretch for tens of thousands of light years. These patterns reveal how the galaxy evolved, how it rotates, and how gravity shapes every part of it. When we map the stars we uncover a structure far more ordered and complex than what we see in photographs. The stars move in carefully organised paths that trace the shape of the spiral arms and reflect the invisible structure of the dark matter halo. The inner part of Andromeda has one of the highest concentrations of stars in the local group. The central bulge contains older stars, tightly packed together, glowing in warm, reddish light. Their orbits are fast and chaotic, shaped both by the dense mass of the bulge and by the supermassive black hole at the centre. These stars move so quickly that their combined motion creates a smooth glow rather than distinct points of light. If you were inside that region, you would be surrounded by a sky full of countless bright stars, far more than we see from Earth. Night would never be truly dark. The crowding of stars in Andromeda's core is one of the strongest indicators of its scale. As you move outward from the core, the stars begin to spread out, forming the well-known spiral arms. These arms are not just decorative features, they are regions where the density of stars increases due to waves of gravitational compression. These spiral patterns are massive structures extending across tens of thousands of light years. Within them, stars form in large clusters when gas clouds collapse. Bright young stars give the arms their blue glow, reveal areas where star formation is most active. The arms curve through the disk in elegant arcs that show how the galaxy rotates. This rotation is not uniform. Stars closer to the centre orbit more quickly, completing a loop in a shorter time. Stars farther out move more slowly, but the surprising fact is that the outer stars still orbit faster than expected. If Andromeda contained only the matter we can see, the outer disk would rotate more slowly and eventually fly apart. But the rotation stays strong because of the hidden mass in the halo. This hidden mass explains why the spiral arms do not unravel and why Andromeda maintains its shape despite its size. Between the arms lie vast regions where stars are older and more spread out. These regions appear darker and less structured, but are filled with stars quietly orbiting the galaxy's centre. The contrast between star-forming arms and older regions gives Andromeda a layered appearance, with bright and dim zones that reveal different stages of stellar evolution. The galaxy is like a massive city, with busy regions full of activity and quieter sections where older residents remain. Beyond the main disk, the stellar distribution becomes even more fascinating. Andromeda has a thick disk, a region above and below the main spiral where stars orbit in slightly tilted paths. These stars are older and have higher velocities, suggesting that they were formed during an earlier, more chaotic period of Andromeda's history. Some were likely captured from smaller galaxies during mergers. The thick disk is subtle when viewed from a distance, but when studied closely, it adds another layer to the galaxy's scale. It extends for thousands of light years above and below the main disk, creating a three-dimensional structure far larger than the flat spiral we imagine. Then comes the halo, where the stellar distribution becomes extremely sparse. Even though the halo stretches hundreds of thousands of light years in every direction, its stars are spread so thinly that you would travel enormous distances before encountering one. These halo stars are among the oldest in the galaxy, formed during its earlier stages or captured during ancient mergers. They orbit in long looping paths that take them far above and below the disk. Their presence reveals that Andromeda is not simply a flat structure floating in space. It is a massive sphere of influence with stars scattered throughout its extended halo. This halo also contains many globular clusters. These dense clusters of hundreds of thousands of stars are some of the oldest surviving structures in the galaxy. Andromeda has more than 450 globular clusters, making it one of the richest collections in the local group. Each cluster is a bright, compact ball of stars orbiting the galaxy like tiny satellites. Some follow tight orbits close to the disk. Others travel in sweeping arcs far into the halo. These clusters help scientists measure Andromeda's mass and map the structure of its gravitational field. One of the most surprising discoveries about Andromeda's stellar distribution came from the faint streams extending from the galaxy. These streams are made of stars pulled from dwarf galaxies as they were torn apart by Andromeda's gravity. They trace long arcs through the halo, some stretching for tens of thousands of light years. These streams show how the galaxy grows. They reveal past collisions and mergers, acting as fossils of Andromeda's violent history. These stellar streams also show that Andromeda's true shape is more complex than a simple spiral. The halo is irregular and uneven, shaped by the remnants of past galaxies. Some parts of the halo are denser than others. Some have faint arcs or waves. These structures are clues to Andromeda's past, revealing the paths of galaxies it absorbed long ago. This entire distribution of star, from the crowded core to the spiral arms, the thick disk, the halo, the streams, shows how enormous Andromeda really is. Its structure extends far beyond the light we see in telescopes. It contains stars spread across hundreds of thousands of light years, each one moving according to the galaxy's gravity. The stars themselves reveal the full scale of the galaxy. By studying their motion and distribution, we can map Andromeda's shape, mass, and history. The distribution of stars across Andromeda becomes even more revealing when we look at how different populations of stars trace different eras of the galaxy's life. In the central bulge, the oldest stars dominate, glowing with a steady red light. These stars formed early in the galaxy's history, when Andromeda was still assembling itself through rapid bursts of star formation and violent collisions. Many of these stars have been burning for more than 10 billion years. Their presence shows how ancient Andromeda is and how much time was required to build a galaxy of such immense size. These stars are survivors of a younger universe, and they orbit the center at high speeds because the region around the core contains so much mass. Moving outward, the stars in the spiral arms tell a very different story. They are younger, brighter, and often more massive. The spiral arms are factories for new stars. They compress gas clouds and trigger star formation as they rotate. This creates bright clusters that glow blue because young, hot stars emit more energetic light. These regions change constantly as new stars ignite and older stars drift away. The arms look beautiful in photographs because they shine with the light of millions of young stars. But this beauty also reveals the galaxy's restless nature. Andromeda is constantly renewing itself, building new generations of stars even as older ones fade. The contrast between these young and old stars shows how gravity organizes the galaxy. The central regions are dominated by mass, while the spiral arms reflect the ongoing process of star formation. The thick disk reveals a transitional population, stars that are older than those in the arms, but younger than those near the core. Their positions and motion show how Andromeda evolved after its early chaotic mergers, but before its spiral structure settled into the shape we see today. The galaxy's thick disk is like a fossil layer in geology, recording a quieter, more stable period when Andromeda began to take on a recognizable form. Beyond the disk, the halo reveals the true scale of the galaxy's history. The stars in the halo are ancient and widely scattered, some of them likely formed in dwarf galaxies that Andromeda absorbed long ago. Their strange orbits, some tilted, some elongated, show that they do not belong to the original disk. They were imported into Andromeda during mergers. Their presence proves that the galaxy we see today is the result of countless interactions. Andromeda did not grow alone. It grew by consuming others, adding their stars to its halo and their gas to its disk. This process continues even now, as dwarf galaxies orbit the halo and slowly stretch into streams under Andromeda's gravitational pull. These stellar streams are among the most powerful pieces of evidence for Andromeda's enormous scale. They stretch across the halo in arcs so long that it can take thousands of years to cross them. Some streams wrap around the galaxy multiple times. Others are faint and diffuse, barely visible even to modern telescopes. These streams are the remains of destroyed galaxies, pulled apart by Andromeda's gravity and stretched into thin lines. Each stream maps the path of a galaxy that once existed on its own. The fact that Andromeda contains so many streams shows how long and active its history has been. Few galaxies have experienced as many mergers or consumed as many companions. Even the dwarf galaxies that still survive show the galaxy's scale. Some orbit close to the halo. Others travel in wide, looping paths far beyond the disk. Their orbits reveal the shape of the dark matter halo, which extends far beyond the visible stars. The dwarfs move along curved paths that bend according to the halo's gravity. Some follow a flat plane, while others orbit at steep angles. These patterns show that Andromeda's influence stretches in every direction. The galaxy is not just wide, it is deep. Its gravitational field fills a massive volume of space, shaping the motion of dozens of smaller galaxies. If you placed yourself somewhere inside the halo, far above the disk, the view would be staggering. Andromeda would stretch below you like a glowing wheel, with its spiral arms forming a bright, swirling pattern around the core. The disk would be thin, glowing like a band of light across the darkness. The halo would appear as faint scattered stars drifting in every direction, with occasional bright globular clusters shining like jewels. You would see dwarf galaxies hanging in the distance, small and dim compared to the massive spiral below. Every part of the view would remind you how enormous the galaxy is, and how tiny the stars appear when spread across such an immense volume of space. Back on Earth, we see none of this richness. Andromeda appears small because it is distant. The faint patch in the sky is merely the bright inner core, not the full galaxy. We see only the concentrated light of stars tightly packed near the centre. The arms, the halo, the streams, the clusters, and the dwarfs are all too faint for the naked eye. The galaxy we know is just the tip of something far larger. If you removed the darkness and revealed every star, Andromeda would fill a vast portion of the night sky. Its disk would appear as a wide, soft glow, and its halo would stretch outward like a mist of stars. The galaxy would dominate our view, reminding us how close and how enormous it truly is. The scale of Andromeda becomes even more impressive when we look at how much space exists between stars inside the galaxy. Even though Andromeda contains up to 1 trillion stars, they are spread across such a large volume that space within the galaxy is mostly empty. The average distance between stars is several light years. If you lived on a planet inside Andromeda, the night sky would look similar to ours. You would see stars scattered across the sky, not packed tightly together. The galaxy looks dense in images only because we see it from so far away that millions of stars blend together visually. This emptiness is essential for understanding the future collision of Andromeda and the Milky Way. When the galaxies merge, few stars will collide directly. The galaxies will pass through each other, and their shapes will distort due to gravity, but the stars themselves will remain mostly untouched. This is possible only because galaxies are so large and their stars so spread apart. The merger will create a new galaxy, but most stars will simply fall into new orbits. This shows once again that the true scale of a galaxy cannot be understood just by counting stars. The space between them is just as important. When we put everything together, the central bulge, the spiral arms, the thick disk, the halo, the clusters, the streams, the dwarfs, the full scale of Andromeda comes into focus. It is not only wide, it is deep, tall, old, massive, and dynamic. It fills a huge portion of the local group, shaping the motion of nearby galaxies. It carries the remnants of ancient systems within its halo. Its core holds billions of old stars packed tightly together. Its arms are alive with star formation. Its halo stretches farther than we can easily imagine. Every part of Andromeda shows a scale that challenges our intuition. The true scale of Andromeda becomes even more striking when we explore its gas and dust, the raw materials that build future stars. These components stretch across the entire galaxy, woven through its arms and scattered through the halo. They form enormous clouds that dwarf anything found in our solar system. These clouds are so large that light takes years to cross them. Some contain enough material to create thousands of stars. Others drift quietly for millions of years before collapsing to ignite new light. The presence of so much gas and dust shows how active Andromeda still is. It is not a dying galaxy. It is one that continues to grow, continues to recycle material, and continues to shape new generations of stars. The gas inside Andromeda exists in several forms. Some of it is cold and dense, forming dark clouds that are nearly invisible even to powerful telescopes. These clouds are the birthplaces of stars. When gravity compresses them, they fragment into smaller pockets. Each pocket collapses until nuclear fusion begins, creating a new star. These star-forming regions fill the spiral arms of the galaxy, especially in places where the gas is pushed together by density waves traveling through the disk. The result is a pattern of glowing blue clusters, young stars shining brightly against the darker background of older stars. Other gas is warmer and more diffuse, filling the spaces between stars. This gas glows faintly in certain wavelengths of light, revealing enormous structures spread across thousands of light years. Some of these regions are leftovers from ancient supernova explosions. When massive stars die, they release shock waves that push gas outward, creating bubbles and shells. These structures act as markers of past activity. They show where massive stars once lived and died. They show how Andromeda's past continues to influence its present. The dust inside Andromeda plays a different role. Dust particles are tiny, smaller than grains of sand, but they collect into massive lanes that weave through the spiral arms. These lanes absorb starlight, creating dark streaks across the galaxy. They cool the gas, helping it collapse into new stars. They also scatter light in ways that reveal the shape of the galaxy's arms and the structure of its disk. In some places, the dust forms thick clouds so dense that they hide entire regions of stars behind them. If you travelled inside Andromeda, these dust lanes would appear as dark, murky regions, blocking your view of the galaxy beyond. Together, the gas and dust reveal a galaxy still in motion. They show where stars are being born, where they have died, and how their remnants shape the next generation. They show how Andromeda evolves over billions of years, one cloud at a time. The presence of this material also reinforces the galaxy's scale. These clouds are not small pockets of gas floating in a confined area. They stretch across tens or hundreds of light years. Their boundaries fade into the darkness. Their motion is slow but immense, driven by the galaxy's rotation and by the gravity of nearby stars. One of the most striking things about Andromeda's gas is how far it extends beyond the visible disk. Modern observations reveal a huge envelope of gas spreading hundreds of thousands of light years from the galaxy's centre. This gas is extremely thin, far thinner than any atmosphere on Earth, but it contains enormous amounts of mass due to its size. It fills a significant portion of the galaxy's halo, blending with gas stripped from dwarf galaxies and gas expelled by ancient supernova. This extended gas envelope shows that Andromeda is not confined to its bright disk. Its influence reaches far beyond the regions we can easily observe. The halo gas also interacts with Andromeda's dark matter. While dark matter does not directly collide with gas, its gravity shapes how the gas moves. This interaction creates subtle flows across the halo, slowly pulling gas inward over billions of years. Some of this gas eventually reaches the disk, replenishing the material needed to form new stars. This process ensures that Andromeda does not run out of star-forming gas quickly. It keeps the galaxy alive, maintaining a steady pace of star formation across cosmic time. Within the disk, the gas forms beautiful patterns that trace the galaxy's rotation. These patterns show how fast the spiral arms move relative to the rest of the disk. They also reveal turbulence in the gas, created by shock waves from supernova and by the gravitational influence of star clusters. These motions are slow compared to human timescales, but over millions of years, they create dramatic changes in the galaxy's structure. Gas clouds drift through the arms, collapse into stars, and eventually disperse again when those stars die. Andromeda is constantly reshaping itself through this cycle. The presence of all this gas also means that Andromeda is far from reaching its final form. Galaxies slowly change as their gas supply dwindles. When a galaxy exhausts its gas, star formation slows and eventually stops. Andromeda is not at that stage. It still contains enough gas to continue forming stars for billions of years. Even after its future merger with the Milky Way, the combined galaxy will have enormous reserves of gas that will ignite new waves of star formation. This long-term activity adds another dimension to Andromeda's scale. It is not only huge in space and time, it is also a galaxy with a long future ahead of it. When we study the gas and dust inside Andromeda, we begin to understand how complex a galaxy truly is. It is not just a collection of stars, it is a dynamic ecosystem filled with energy, motion, and continuous transformation. Each cloud plays a role. Each shockwave reshapes its surroundings. Each supernova returns enriched material to the galaxy. Over billions of years, these processes build the structures we see today. The true scale of Andromeda's gas becomes even clearer when you consider how much of it exists and how far it spreads. The visible spiral arms show only the densest areas. Most of the galaxy's gas is hidden in diffuse layers stretching across the entire disk and far into the halo. Some regions contain hydrogen that is so thin that a spaceship flying through it would encounter almost nothing. Yet when viewed across hundreds of thousands of light years, this gas adds up to enormous mass. These vast, delicate structures are one of the reasons Andromeda continues forming stars. They provide a slow but steady supply of raw material that can feed star formation for billions of years. This gas does not float freely. It moves in complex patterns shaped by gravity, rotation and temperature. In the spiral arms, gravity compresses gas into dense clumps. These clumps collapse into new stars, but the energy released during star formation, especially from massive stars, can push surrounding gas outward. This creates bubbles and cavities scattered across the arms. If you could see Andromeda from inside one of these bubbles, you would find yourself surrounded by faint glowing walls of gas lit by the powerful radiation of nearby stars. These structures reveal how star formation sculpts the galaxy from within. Supernova explosions contribute even more dramatically to this process. When massive stars reach the end of their lives, they explode with tremendous energy, sending shockwaves through nearby clouds. These waves compress gas in some regions and disperse it in others. The result is a cycle of destruction and renewal. One generation of stars creates the conditions for the next. This ongoing cycle is what keeps Andromeda active. Without it, the galaxy would slowly fade as older stars die and no new ones take their place. Beyond the spiral arms, the gas in the outer disk is colder and more stable. It drifts in broad lanes shaped by the galaxy's rotation. These outer regions show fewer signs of star formation, but remain important because they act as reservoirs of gas for the future. Over long timescales, gas from the outer disk flows inward, replenishing the inner regions. This inward flow is incredibly slow, taking hundreds of millions of years. But without it, Andromeda would eventually run out of fuel for new stars. The fact that such a flow exists shows how interconnected the galaxy's structures are. Nothing moves independently. Every part influences every other part. The halo gas adds yet another layer. This gas is incredibly diffuse, so thin that even within a cubic meter, you would not find a single atom. But across the halo's massive volume, this gas becomes significant. It contains metals expelled by ancient stars, as well as material stripped from dwarf galaxies. It connects Andromeda to the intergalactic medium beyond. Some of this gas may even escape into the space between galaxies, while other portions fall inward toward the disk. This constant exchange helps regulate the galaxy's evolution. Even the emptiest parts of the halo play a role in shaping the galaxy's future. If you could observe Andromeda in ultraviolet or X-ray light, the gas would become visible in ways it is not at optical wavelengths. You would see giant hot regions glowing brightly near the centre, where supernova explosions and energetic stars heat the gas to extreme temperatures. You would see cooler, denser lanes in the spiral arms, outlined by shadows in the hot gas. You would see faint filaments extending into the halo, connecting the galaxy to its surroundings. This multi-layered gas structure stretches far beyond the visible disk, showing that the galaxy is not merely a flat spiral, but a vast, three-dimensional object filled with material at all temperatures. Another remarkable feature of Andromeda's gas is the presence of chemical elements heavier than helium, elements created inside stars and spread throughout the galaxy when those stars die. These heavier elements become part of dust grains, join new gas clouds, and eventually form new stars and planets. This recycling process has been happening for billions of years in Andromeda. It means that planets forming in the galaxy today contain ingredients from stars that lived and died long before the Sun existed. The entire galaxy is connected by this flow of material, a continuous chain from one generation of stars to the next. Dust plays a similar role. Dust grains absorb light, cool gas, and help it collapse into new stars. Dust often collects in the densest regions of the galaxy, forming long dark streaks across the spiral arms. These dust lanes are some of the most recognizable features of Andromeda in telescope images, but they're even more impressive when studied closely. Some lanes stretch for hundreds of light years, weaving in and out of the spiral arms like tangled threads. These lanes reveal the structure of the galaxy's magnetic field as well, because dust grains often align with magnetic forces. This creates subtle patterns in the light we observe, giving scientists clues about the invisible field shaping the galaxy. As the gas and dust move through the disk, they create subtle ripples in the structure of the galaxy. These ripples sometimes appear as faint waves in the spiral arms. In other places, they create slight warps in the disk itself. These distortions show that Andromeda is responding not only to its internal forces, but also to gravitational interactions with dwarf galaxies. When a smaller galaxy passes close to Andromeda, it can tug on the disk and create lasting shapes that remain for millions of years. Even tiny gravitational disturbances leave visible marks when the galaxy is as large as Andromeda. The gas dynamics also reveal how the galaxy reacts to the approaching Milky Way. Though the collision is billions of years away, the galaxies are already tugging on each other slightly. This tug affects the motion of the outer disk, creating asymmetries in the distribution of gas. Some regions appear thicker, while others are more diffuse. These subtle changes are early signs of a much larger interaction on the horizon. Andromeda may be far away, but its future with the Milky Way is already shaping its structure. Everything we see in Andromeda's gas and dust, every lane, every bubble, every filament, shows us how enormous the galaxy truly is. These structures stretch across space in ways that dwarf anything in the Milky Way's local neighborhood. They reveal a galaxy filled with motion and energy, shaped by billions of years of evolution and preparing for billions more. Together, the stars, gas, dust, and dark matter create a galaxy that is far more complex and far more massive than the faint glow we see in the sky. Andromeda's true scale is written not just in its size, but in the depth of its structure and the richness of its history. It is a colossal system of interconnected parts, each one influencing the next, forming a galaxy that spans hundreds of thousands of light years and continues to evolve across the vast stretches of time. The true scale of Andromeda becomes even more overwhelming when we look beyond the structures inside the galaxy and examine how it fits into the larger architecture of the universe. A galaxy is not an isolated object floating alone in space. It exists as part of a much bigger cosmic environment, connected by gravity to other galaxies, linked through invisible bridges of dark matter, and shaped by the expansion of the universe itself. Andromeda is massive, but it is also a single piece in a far greater puzzle. When we place it in that larger context, its scale grows even more immense. Within the local group, Andromeda is the largest and most dominant galaxy. The Milky Way is slightly smaller, but the two are similar enough that they control the motion of every smaller galaxy around them. Dozens of dwarf galaxies orbit the local group, some belonging to Andromeda, others to the Milky Way. These dwarfs follow complex paths shaped by the gravitational pull of the two spirals. Many are caught in between, drifting slowly through the empty regions, separating the two giants. This entire system spans more than 10 million light-years and is bound together by gravity. Andromeda sits near the center of this structure, anchoring it with its enormous mass. The local group itself is part of an even larger structure called a galaxy filament. These filaments are the largest formations in the universe, stretching hundreds of millions of light-years. They are made of countless galaxies connected by threads of dark matter. Andromeda lies along one of these filaments, linked to neighboring groups and clusters across immense distances. Even though the galaxy seems isolated in photos, it is one point in a vast cosmic web, a network of galaxies stretching through the universe, like threads woven into a massive cosmic fabric. This web structure reveals the universe's true scale. Galaxies like Andromeda form along the densest threads of dark matter. Their positions are not random. They grow where gravity pulls matter together. Over billions of years, these regions accumulate enough mass to form galaxy groups and clusters. Andromeda exists because of this structure. Its formation, growth, and present shape are all connected to the dark matter web beneath it. When we observe Andromeda's position in this web, we see how its true scale goes far beyond its physical size. It influences galaxies across tens of millions of light years. It participates in the motion of the local group as it falls slowly toward the Virgo cluster, an enormous collection of galaxies far more massive than anything in our immediate region. Andromeda, the Milky Way, and all surrounding dwarfs are drifting together toward this cluster. The motion is slow on human timescales, but immense across cosmic distances. If you could watch the universe over billions of years, you would see Andromeda drifting not just toward the Milky Way, but toward Virgo, and beyond that, toward an even larger gravitational region called the Laniakea supercluster. This massive structure contains hundreds of thousands of galaxies spread across 500 million light-years. The local group, including Andromeda, is just a tiny part of this structure. Even more astonishing, Laniakea is not the end. It is connected to other superclusters by the cosmic web. The universe is arranged in a pattern of webs, sheets, and voids that stretch to the horizon of what we can observe. Against this backdrop, Andromeda is huge, but also tiny. Its trillion stars are only a small fraction of the stars in Laniakea. Its dark matter halo is enormous, but superclusters contain far more mass. Its 220,000 light-year diameter is impressive, but cosmic filaments stretch millions of light-years. This contrast makes Andromeda's true scale feel even more powerful, because it shows that even the largest structures we can see with the naked eye are part of a universe far more immense than we can comprehend. The empty regions around Andromeda reveal just as much about its scale. Galaxy clusters and filaments are separated by vast voids, enormous pockets of space where few galaxies exist. These voids can be hundreds of millions of light-years wide. Andromeda lies near the edge of such a void. This emptiness tells us how galaxies are distributed and how rare the bright structures truly are. If you travelled away from Andromeda in the wrong direction, you could drift for hundreds of millions of light years without encountering another massive galaxy. This contrast between crowded regions and empty voids emphasizes how significant Andromeda's brightness and mass truly are. When scientists measure Andromeda's motion across the cosmic web, they see subtle shifts in its velocity that hint at much larger gravitational forces. These forces stretch across the universe, shaping the movement of galaxies and determining their future paths. Even the approaching collision between Andromeda and the Milky Way is influenced by the cosmic web. Gravity from surrounding structures tugs on both galaxies slightly, adjusting their trajectories over billions of years. This connection to larger structures also affects Andromeda's internal evolution. Galaxy mergers are more likely in regions where galaxies are packed close together along filaments. Andromeda's past shows that it lived in such a region. It absorbed dwarf galaxies, formed new stars, and grew its halo as the cosmic web guided material towards it. Had Andromeda formed in a different part of the universe, in a cosmic void instead of a dense filament, it might have remained much smaller. Its present scale reflects not only its internal processes, but also its position within the web of the universe. Understanding Andromeda's role in this cosmic architecture allows us to see how deeply connected galaxies are. They do not form in isolation. They emerge along invisible patterns of dark matter. They evolve through mergers and interactions guided by the cosmic web. They drift together, pulled by the same distant gravitational sources. Andromeda's scale is not simply physical, it is relational. Its significance comes from how it fits into the universe's grand design. The cosmic web surrounding Andromeda gives the galaxy a kind of gravitational identity that goes far beyond its visible form. Even though we think of Andromeda as a single object, it is actually part of a continuous flow of matter shaped by dark energy and dark matter. Every galaxy in the local group sits inside this flow, drifting along paths carved by the deepest gravitational wells. Andromeda's position means it draws material toward itself while also being pulled by far larger structures. When we understand this context, the galaxy's true scale expands from hundreds of thousands of light years to hundreds of millions. One way we see this is through the motion of smaller galaxies around Andromeda. These dwarfs follow orbits that reveal the shape of the dark matter web. Their paths are not smooth circles but elongated loops, arcs and spirals influenced by both Andromeda's halo and the gravity of the Milky Way. The smaller galaxies act like test particles, showing us the invisible architecture of the region. Some dwarfs orbit in the same plane, suggesting they arrive together as part of a larger structure. Others move in random directions, showing Andromeda's long history of mergers and captures. Each orbit reflects the galaxy's enormous mass and the reach of its gravitational field. Beyond the local group, Andromeda participates in the motion of the entire Laniakea supercluster. The galaxies in this structure drift slowly toward a region known as the Great Attractor, an area so massive that it pulls entire clusters toward it. This motion is subtle, but when measured across hundreds of millions of years, it becomes dramatic. Andromeda, the Milky Way, and all surrounding galaxies fall together toward this distant gravitational anchor. This movement reminds us that galaxies are not stationary structures. They are passengers inside an ever-changing universe, shaped by forces far beyond their individual scales. The empty voids near the local group offer another perspective on Andromeda's scale. These voids contain almost no galaxies. They stretch across enormous distances, creating huge gaps in the cosmic web. The local group sits near the boundary of one such void. This means Andromeda is part of a rare region where matter is dense enough to form large galaxies. If our galaxy and Andromeda were located deeper inside the void, neither would have grown to their current size. The availability of nearby matter and the structure of the cosmic web determine how large galaxies can become. Andromeda's impressive mass is a direct result of forming in a region rich in material. Even the future collision between Andromeda and the Milky Way reflects their shared place in the cosmic web. Their halos already overlap subtly because the dark matter around them is part of the same larger structure. The motion bringing them together is influenced by forces both local and distant. When the galaxies eventually merge, the event will not be a simple two-body interaction. It will be part of a greater gravitational flow, extending across millions of light years. The new galaxy formed from their merger will continue drifting through the supercluster, shaped by forces that began long before either galaxy existed. This larger context highlights an important truth. Andromeda's true scale is not limited to the stars we see or the gas we detect. It includes its position in a network of galaxies, its relationship to the Milky Way, its connection to the cosmic web, and its role in the motion of an entire supercluster. The galaxy is a node in a system far larger than itself. Its influence stretches across millions of light years, and its future is tied to structures even more massive. If you could step far outside the local group and watch from a vantage point millions of light years away, Andromeda would appear as a bright point in a chain of galaxies. You would see the Milky Way beside it, the dwarf galaxies orbiting both, and the faint threads of dark matter connecting them. You would see the entire group drifting as one, slowly pulled toward the Virgo cluster. From that perspective, Andromeda would look small, but you would know that inside that single point of light lies a galaxy spanning more than 200,000 light years, containing 1 trillion stars, a vast halo, streams of ancient material, and a deep gravitational well shaping everything around it. That contrast, Andromeda looking tiny from afar, yet being enormous up close, is one of the most important insights into its true scale. The universe is structured in layers. Each layer contains giants that look small from the next layer up. Andromeda is a giant within the local group, but from the viewpoint of a supercluster, it is only one part of a much larger arrangement. Yet despite this cosmic vastness, Andromeda remains incredibly significant to us. It is our nearest large neighbour. It is the most detailed spiral galaxy we can study beyond the Milky Way. It gives us a preview of our own galaxy's future. It shows us how galaxies evolve, how dark matter shapes them, how gas fuels them, and how mergers transform them. Its size and structure make it a laboratory for understanding the universe. When we study Andromeda, we do not simply learn about a single galaxy. We learn about how galaxies live, how they change, and how they fit into the universe's enormous architecture. We learn about the forces shaping their motion across cosmic space. We learn about the deep patterns hidden beneath the glow of stars, and most importantly, we learn how small we are compared to the structures that surround us. For all its greatness, Andromeda is just one galaxy among trillions. But because it's close enough for us to examine it in detail, it becomes our doorway into understanding the universe's true scale. It stands above us every night, faint and quiet, hiding a size beyond comprehension. And as we study it piece by piece, its stars, its gas, its halo, its history, its motion, we reveal the story of a galaxy that spans unimaginable distances and connects to structures even larger than itself. The true scale of Andromeda becomes even more remarkable when we examine the role of dark matter in shaping every part of the galaxy. Without dark matter, Andromeda would not exist in its current form. Its spiral arms would fall apart, its halo would collapse, and its stars would drift into intergalactic space. Dark matter is the invisible scaffolding holding the galaxy together, forming a structure far larger than the bright disk we can see. This structure stretches hundreds of thousands of light years beyond the visible regions and contains most of the galaxy's total mass. Andromeda's stars, gas and dust make up only a small percentage of its true weight. The rest is hidden in a halo we cannot see, but whose presence shapes every motion within the galaxy. This halo is not smooth or uniform. It is an enormous, dynamic field filled with clumps and substructures formed by ancient mergers. Each clump is a remnant of a galaxy that Andromeda absorbed long ago. When a dwarf galaxy falls into Andromeda, its stars are stripped and stretched into long streams, but its dark matter becomes part of the halo. Over time, as hundreds of such mergers occurred, Andromeda's halo grew into one of the largest in the local group. The halo extends so far that its outer edges nearly touch the Milky Way's halo. Even though the galaxies are still millions of light years apart, their dark matter halos already interact gently, revealing how truly enormous these invisible structures are. The shape of the halo determines how Andromeda rotates. When astronomers measured the speeds of stars in the outer regions, they expected the rotation to slow down as the distance from the center increased. Instead, the rotation remained fast. This flat rotation curve is one of the clearest signs of dark matter. The only way to keep stars in such wide orbits without drifting into space is to surround the galaxy with an enormous amount of unseen mass. This mass creates a gravitational field strong enough to hold the galaxy together. Without dark matter, the outer disk would unravel over time. Instead, it remains stable across billions of years. The halo also influences how stars form inside the galaxy. Its gravity compresses gas clouds in some regions while stretching them in others. This creates patterns of star formation across the spiral arms. Some arms become more active because the halo's gravitational pull enhances the density waves moving through the disk. Other regions become quieter as the halo stabilizes the motion of gas. These subtle effects are not visible directly, but they shape the bright and dark structures across Andromeda. Another important role of the halo is regulating how dwarf galaxies move around Andromeda. These dwarfs orbit through the halo, tracing its structure like birds circling around an invisible mountain. Some follow tight orbits, while others take long elliptical paths that stretch tens of thousands of light years into space. Their motion reveals the distribution of dark matter. By tracking these orbits, scientists can map the shape of the halo and determine where its density increases or decreases. This mapping shows a structure far more complex than a simple sphere. It contains distortions, clumps and streams that reflect Andromeda's long history of absorbing smaller galaxies. Dark matter also affects Andromeda's future merger with the Milky Way. When the two galaxies eventually collide, their halos will interact long before their disks meet. The halos will blend and distort, pulling the galaxies toward each other faster than their visible stars would suggest. This early interaction will create gravitational tides that stretch both galaxies, altering their shapes even before the first stars pass through each other. The halos will merge completely long before the visible parts of the galaxy settle into a new shape. This process shows how much of Andromeda's scale is hidden. The galaxy's visible disk is only the tip of a much larger structure. Even the shape of Andromeda's halo tells a story about the galaxy's past. Some regions of the halo are thicker or denser than others, suggesting that Andromeda experienced major mergers in its early history. One such event may have occurred billions of years ago when a large dwarf galaxy plunged into Andromeda and merged with its disk. This collision may have created waves and ripples still visible in the halo today. These features are so faint that they can only be detected with careful measurements, but they extend across enormous distances, sometimes wider than the bright part of the galaxy itself. Each ripple marks a moment in Andromeda's past, frozen in space like a fossil. Dark matter also determines how long Andromeda will remain active. As the galaxy continues to move through space, it pulls in gas, dust, and dwarf galaxies from its surroundings. Much of this material is guided by the dark matter halo. The halo shapes the galaxy's gravitational influence, determining which objects fall toward it and which drift away. This ongoing process allows Andromeda to continue growing slowly even now. The galaxy may seem quiet from a distance, but it is still accumulating mass, still reshaping itself, and still preparing for its eventual merger with the Milky Way. Understanding Andromeda's dark matter halo gives us a deeper sense of its true size. The visible disk spans more than 220,000 light-years, but the halo extends far beyond that. Some estimates reach over 1,000,000 light-years. This means Andromeda's influence covers a region of space so large that if you travelled at the speed of light, it would take you years just to cross the halo alone. The visible galaxy is only a small glowing island surrounded by a vast invisible ocean of gravity. The presence of dark matter transforms Andromeda from a galaxy into a gravitational landscape, far more extensive than its visible form suggests. If you could somehow see dark matter, Andromeda would not appear as a glowing spiral with faint outer regions. It would appear as an enormous sphere, wide and thick, dwarfing the bright disk at its centre. The visible galaxy would look like a tiny core inside a massive transparent cloud. This cloud is where most of the galaxy's mass resides. It shapes everything from the motion of stars to the paths of distant dwarf galaxies, drifting at the edges of the halo. One of the clearest demonstrations of Andromeda's dark matter halo comes from the behaviour of satellite galaxies that orbit it. Some of these satellites move in a flat, coordinated plane. Others orbit in random directions. Their distribution is uneven because the halo itself is uneven. Each satellite traces a different part of the gravitational field. When they drift through denser regions of the halo, they speed up. When they move through thinner areas, they slow down. Their motions create a map of the invisible mass surrounding Andromeda. This map shows a structure that is not smooth but full of ridges and valleys, subtle gravitational waves frozen in space. These waves exist because Andromeda has absorbed so many smaller galaxies over time. Each merger adds new lumps of dark matter to the halo. Sometimes these lumps dissolve smoothly. Other times they maintain their structure for billions of years, drifting through the halo like invisible islands. When stars and dwarf galaxies pass near these lumps, their paths bend slightly. These deflections reveal the presence of structures we cannot see directly. Andromeda's halo is not simply large, it is complicated, layered, and shaped by ancient events that took place long before the Sun formed. Another striking sign of the halo's influence is the stability of Andromeda's spiral arms. Spiral arms are delicate structures. In a galaxy without dark matter, the arms would slowly unwind or collapse. But in Andromeda, the dark matter halo keeps the rotation curve flat enough to preserve the spiral shape. It keeps the arms moving at consistent speeds across vast distances. This stability allows the galaxy to maintain its form over long periods. The arms may shift their exact positions over millions of years, but the overall structure remains intact because the halo supports it. The halo also determines how the galaxy interacts with its surroundings. When Andromeda moves through intergalactic space, the halo acts like a giant gravitational net. It pulls loose gas, stray stars, and small galaxies toward the center. Some of this material is absorbed, some is stretched into streams, some falls into stable orbits. This process shows that Andromeda is not a closed system. It is constantly interacting with the space around it, gathering new material and adding it to its mass. Over billions of years, this slow accumulation shapes the galaxy's scale even more. As we look further into Andromeda's halo, we find that its edges are difficult to define. The density of dark matter decreases gradually rather than sharply. There is no clear boundary marking where the galaxy ends. Instead, the halo blends into the intergalactic medium. This blending means Andromeda's true size is somewhat ambiguous. It depends on how we measure its mass, how we define its influence, and how we interpret the faint signals from distant stars. But no matter how we measure it, the halo is far larger than the visible disk. The galaxy's mass and reach extend across millions of light years, shaping not only its internal structure, but the entire region around it. This enormous halo has deep implications for the future collision between Andromeda and the Milky Way. The halos of the two galaxies will begin interacting long before the visible parts touch. As the halos merge, they will slow the galaxy's approach and create gravitational tides that stretch their shapes. These tides will alter the motion of stars in both galaxies, sending some into new orbits and others into intergalactic space. The merging halos will also determine the final structure of the new galaxy that forms after the collision. Without dark matter, the merger would look completely different, but with dark matter, the process becomes a slow blending of two massive invisible structures, guiding the visible stars like passengers inside a much larger framework. The halo also influences Andromeda's relationship with the cosmic web. Filaments of dark matter connect the galaxy to its neighbours, forming pathways that guide the flow of material. Through these connections, Andromeda receives gas and even occasional dwarf galaxies that move along the filaments. These pathways also explain why Andromeda formed in the first place. Galaxies grow at the intersections of filaments because those regions contain the most matter. Andromeda sits at one of these intersections, which is why it became so large. Its halo is not just a product of internal processes, it is shaped by the entire cosmic web surrounding it. Understanding Andromeda's dark matter halo gives us one of the deepest insights into its true scale. The visible galaxy is only a fraction of the whole. The halo is the real backbone of the system. It determines how stars move, how gas flows, how dwarf galaxies orbit, and how the galaxy will evolve in the future. It stretches across a region so vast that even travelling at the speed of light, it would take years to cross the halo from end to end. Andromeda is far larger, more massive, and more complex than anything we can see with our eyes. From Earth, this enormous structure appears as a faint blur in the night sky. But beneath that faint blur lies a galaxy with 1 trillion stars, a vast halo, the remnants of ancient mergers, streams of captured galaxies, and a gravitational field that stretches across millions of light years. This contrast between what we see and what Andromeda truly is is one of the most powerful reminders of how much the universe hides behind faint points of light. The true scale of Andromeda becomes even more astonishing when we examine the stars that orbit far beyond the visible disk. These distant stars form structures that seem almost detached from the galaxy, but are actually some of the strongest indicators of Andromeda's enormous size. Many of these stars belong to massive tidal streams, long rivers of starlight created when smaller galaxies were torn apart by Andromeda's gravity. Some streams wrap partially around the galaxy, others stretch into deep space. They are faint, fragile, and easy to miss, but together they reveal the violent past that shaped Andromeda into the giant we see today. These streams are not random. They follow paths determined by the galaxy's gravity. When a dwarf galaxy approaches Andromeda, the outer stars of the smaller galaxy are pulled away first. Over time, the entire dwarf dissolves. Its stars stretch into long, thin arcs that follow the dwarf's original orbit. This process can take billions of years, and even after the dwarf is fully absorbed, the stream remains as a memory of where it once travelled. These stellar rivers act like scratch marks etched into deep space, showing how Andromeda has grown over time. One of the largest and most famous of these features is the giant stellar stream. It extends for tens of thousands of light years and is one of the clearest pieces of evidence that Andromeda once consumed a large galaxy. The stream curves beneath the disk in a sweeping arc, glowing faintly with the combined light of millions of stars. If you could look closely from within the halo, the stream would appear as a massive band of stars drifting across the darkness, with its brightest points marking where the original core of the dwarf galaxy was disrupted. This one structure alone demonstrates how powerful Andromeda's gravity is. It can tear apart entire galaxies and scatter their stars across enormous distances. These streams also help scientists measure the shape of Andromeda's halo. By tracking how the stars move through the halo, astronomers can determine where the halo is denser or thinner. Streams that bend sharply reveal regions of strong gravity. Streams that stretch smoothly show more uniform regions. Together, these measurements reveal a dark matter halo that is not only vast but also filled with substructures left behind by ancient mergers. In some regions, the halo is thicker because a large dwarf galaxy was absorbed there. In others, it is thinner because material flowed inward over time. The halo is not a quiet place. It is active, filled with remnants drifting from one region to another. Some of the stars in the halo are not part of streams at all. They formed in Andromeda's earliest days and have been orbiting ever since. These ancient stars follow long, looping paths far above and below the disk. Their orbits are often tilted or irregular, showing that they were shaped by events in the galaxy's youth. If you could plot all these star orbits in 3 dimensions, Andromeda would look less like a neat spiral and more like a tangled cloud with a bright core. This cloud is the halo's stellar population, a faint echo of the galaxy's earliest history. In addition to stars, the halo contains clusters of stars that survived even the most violent events. These clusters, called globular clusters, orbit the galaxy like tiny satellites. Andromeda has hundreds of them, more than the Milky Way. Some clusters are found in the inner regions of the halo, while others are incredibly distant. A few clusters orbit so far away from the disk that they challenge our understanding of where the galaxy truly ends. These clusters show that Andromeda's reach extends far beyond what we see. Their existence implies that the galaxy's gravitational influence stretches hundreds of thousands of light years in every direction. The presence of these distant structures demonstrates that Andromeda is not a clean, orderly system. It is a galaxy built over billions of years through constant collisions and interactions. Each merger left behind debris, and that debris is still visible today. The halo is filled with these signatures, each one telling a part of the galaxy's story. When we observe the halo, we see the scars of Andromeda's growth. We see the remnants of galaxies that no longer exist. We see stars that drifted for billions of years from the places they were born. The halo is a vast ancient archive. If you could travel through Andromeda's halo, the scale of these structures would overwhelm you. You might cross a star stream so faint you barely notice it at first. But as you move along it, you would see more and more stars, all drifting in the same direction. You might pass a globular cluster, shining like a bright beacon in the dark. You might even encounter regions where the number of stars suddenly increases, showing that you are crossing a particularly dense part of the halo. All of this would take place across distances so vast that your journey could last thousands of light years. Andromeda's halo is also important for understanding its future. When the galaxy collides with the Milky Way, many of these streams will be pulled in new directions. Some will stretch even farther as the gravitational forces of both galaxies tug on them. Others will be compressed and blended into the forming elliptical galaxy. The halo will become one of the first regions to merge. Its stars will mix with the Milky Way's halo stars, forming a new, much larger structure. This process will erase some streams, stretch others, and create new ones. The future galaxy will still carry the signatures of its past, but they will be difficult to trace back to Andromeda or the Milky Way. The amount of material in Andromeda's halo is immense. Even though the stars are spread thinly, the sheer volume of the halo means it contains far more stars than one might expect. These stars represent only part of the halo's mass. The rest is dark matter that we cannot see. This invisible mass dominates the halo's structure, shaping the motion of everything within it. The halo is not just a boundary region, it is the core environment that defines the galaxy's gravitational influence. And all of this, streams, clusters, ancient stars, dark matter substructures, forms a vast, three-dimensional shell around the visible galaxy. When you picture Andromeda, it is easy to think of the bright spiral arms as the main structure. But the halo dwarfs the disk in both size and mass. The visible spiral is just the glowing centre of a much larger sphere of influence, stretching across a region so large that it challenges our ability to visualize it. The true scale of Andromeda's outer regions becomes even more astonishing when we consider how these faint structures connect the galaxy to its surroundings. The halo is not merely an extended boundary, it is a region where Andromeda interacts with the rest of the local group. Some of the stars drifting in these remote areas were not born in Andromeda at all. They came from dwarf galaxies that wandered too close. Over time, these dwarfs were stripped apart, adding their stars to the halo. This ongoing process means the halo is constantly changing. New streams appear, old ones disperse, and clusters migrate slowly through the gravitational landscape. The edges of Andromeda are alive with motion, even if that motion is too slow to notice on human timescales. These faint features also reveal how much mass Andromeda has accumulated over billions of years. A galaxy does not produce these streams unless it has pulled in many smaller systems. The size and number of these streams suggest that Andromeda's growth has been intense and long-lasting. It absorbed some dwarfs recently, while others were consumed billions of years ago. The halo is a mixture of old and new material. Some stars have orbits that take them deep into the inner regions. Others stay far away, drifting quietly at the edge of the galaxy's gravitational reach. This diversity shows how complex the galaxy's history has been. Even the star clusters in the outer halo highlight its scale. Some clusters orbit at distances that seem almost disconnected from the galaxy. These remote clusters would be extremely faint from Andromeda's centre, yet they remain gravitationally bound. Their motion shows that Andromeda's influence stretches astonishingly far into space. If you observed one of these clusters from a hypothetical world within the halo, Andromeda itself might appear small and distant, glowing like a large hazy shape across the sky. The fact that such clusters orbit stably reveals how massive the halo must be. The halo also contains regions where matter is distributed unevenly. Some areas have more stars or more dark matter than others. These irregularities are remnants of ancient collisions. When a dwarf galaxy entered Andromeda's halo billions of years ago, it created ripples that spread outward like waves in a pond. These waves can still be detected today. They show up as subtle density variations in the halo. In some regions, the stars move slightly faster. In others, they move slower. These changes are faint, but across the enormous distances of the halo, they create large-scale patterns that reveal how Andromeda evolved. This uneven structure becomes even more dramatic when we look at how Andromeda interacts with galaxies on the edge of the local group. Some of the smallest galaxies orbiting nearby are barely held together. Their stars drift slowly toward Andromeda's halo, pulled by its massive gravitational field. These dwarfs are so fragile that a single pass near the galaxy can tear them apart. Their remains then join the growing population of halo stars. This process is slow, but it never stops. Andromeda continues to gather material even now, adding faint new layers to the halo that will remain for billions of years. One of the most important aspects of the halo is how smoothly it transitions from visible structures to nearly invisible ones. In the bright regions of the disk, the stars are so densely packed that they blend into a glowing band of light. As you move outward, the number of stars decreases, the light becomes fainter. Eventually, the stars are so spread out that you would see more darkness than starlight. But even then, the halo continues. The galaxy does not end where the light ends. Its gravity and dark matter extend far beyond what telescopes can easily detect. To grasp the full scale of the halo, imagine travelling outward from the centre of Andromeda. At first, you would move through crowded regions filled with stars, clusters, and glowing gas. As you move farther, the stars would thin out, but you would still see the spiral arms stretching around you. Eventually, the disk would fade behind you, leaving only isolated stars and scattered clusters. After more light years, even these would become rare. Yet you would still be inside the halo. The galaxy's gravitational pull would still influence your motion. You would still be part of Andromeda's structure, even though almost no stars would appear nearby. This journey would take hundreds of thousands of light years, and even then, you might not reach the edge of the halo. This enormous halo is one of the reasons Andromeda will eventually merge with the Milky Way. The two halos are already touching in subtle ways. Their gravitational fields overlap, creating a shared zone where stars and gas feel the pull of both galaxies. This shared region marks the beginning of the long process that will eventually bring the galaxies together. Even though the visible parts of the galaxies remain far apart, their halos are already beginning to blend. This quiet interaction is a reminder that Andromeda's true scale reaches far beyond what we see in the sky. Everything about these outer regions reinforces the idea that galaxies are far larger than their bright cores suggest. Andromeda's halo extends so far that it transforms the galaxy from a flat spiral into a colossal sphere of influence. Its faint structures reveal a history of collisions, growth, and constant change. Its distant clusters show how far its gravity reaches. Its star streams show how many galaxies it has consumed. And its dark matter halo shows how deeply gravity shapes the universe. Despite appearing as a small blur in the night sky, Andromeda is one of the most massive structures we can directly study. The faint material around it contains as much information as the bright inner regions. It tells the story of how galaxies grow and how they interact with the universe around them. It reminds us that even the emptiest parts of space are shaped by forces we struggle to imagine. And it reveals that Andromeda is not simply a neighbour. It is a giant whose true scale stretches across a vast region of the local group. The true scale of Andromeda becomes even clearer when we examine its central region, where some of the most extreme environments in the galaxy exist. At the heart of Andromeda lies a dense concentration of stars, packed so tightly that their combined glow creates the bright core we see from Earth. This region is far more crowded than anything in our Milky Way's neighbourhood. Stars orbit the centre at incredible speeds, each one pulled by the gravity of billions of others. The density is so high that if an observer lived near the core, the night sky would never be dark. Bright stars would cover the sky in every direction, glowing with a brightness we cannot imagine from our position in the outskirts of the Milky Way. At the exact centre rests a supermassive black hole, millions of times more massive than the Sun. This black hole shapes the motion of everything nearby. Stars whip around it at high speeds, their orbits compressed into tight, fast loops. Some stars come so close to the black hole that tidal forces stretch them as they pass. Others drift too close and are consumed entirely. This black hole is not as active as the most extreme ones found in distant galaxies, but it still plays a central role in Andromeda's structure. Its gravity influences a region far larger than the visible core, helping anchor the entire bulge of old stars. The core itself is not smooth. It contains multiple components, dense star clusters, pockets of rotating gas, and regions where young stars occasionally form. These features show that the centre has been shaped by past mergers. When a smaller galaxy fell into Andromeda, its core may have been dragged inward, merging with Andromeda's central region. The remnants of these events can still be seen today in the form of stellar populations that move differently from the surrounding stars. Some stars in the core rotate in one direction, while others rotate in the opposite direction, revealing a chaotic past hidden behind the bright glow. The bulge surrounding the core contains some of the oldest stars in the galaxy. These stars formed early in Andromeda's history, during a time when the galaxy was still assembling its mass. They have burned steadily for billions of years, providing a quiet contrast to the more active spiral arms. The bulge extends far beyond the central region, forming a dense, rounded structure that merges smoothly into the disk. This bulge holds a huge amount of mass, giving Andromeda its strong gravitational centre. Many galaxies lack such a well-defined bulge, but Andromeda's is large and bright, showing how quickly it grew in its early years. Moving outward from the bulge, the stars become less densely packed, but the disk still holds an enormous number of them. The transition from bulge to disk reveals how the galaxy evolved. The inner disk rotates quickly, shaped by the strong gravity of the bulge and the black hole. This rapid rotation creates stability for the spiral arms. The inner disk stars are older than the stars in the outer arms. They formed during a time when Andromeda's gas was more concentrated, allowing star formation to happen more efficiently. These older stars form a smooth, glowing band that surrounds the bulge like a thick ring. Sometimes gas collects near the central region and ignites new star formation. These episodes are rare, but when they happen, they create young, bright stars near the core. These stars stand out sharply against the older, redder stars around them. Their presence shows that Andromeda's center is not entirely quiet. It still has the ability to create new life, even in one of the most hostile environments in the galaxy. These bursts of star formation are often triggered by gravitational disturbances, either from interactions with dwarf galaxies or from waves of gas pushed inward by the rotation of the disk. The central region also contains gas that spirals slowly toward the black hole. Most of this gas never reaches the event horizon, but it heats up as it falls inward, releasing faint radiation. This glow is one of the main indicators that the black hole is still active. Though it is quiet compared to the monster black holes at the centers of some galaxies, Andromeda's black hole remains a powerful engine of gravity and energy. It shapes the motion of stars around it, influences the structure of the bulge, and leaves subtle marks on the inner disk. As we move farther from the center, the spiral arms begin to dominate the galaxy's appearance. These arms are not fixed structures, but patterns created by density waves moving through the disk. The gas and stars inside the arms move in and out of these waves, creating regions where new stars form. The arms are anchors for much of the galaxy's activity. They hold bright clusters, glowing nebulae, and dense clouds of dust that reveal where stars are actively forming. These arms spiral gracefully outward, stretching tens of thousands of light years into the disk. Their shape is one of the clearest signs of Andromeda's mass and rotation. The disk itself is enormous. It stretches more than 100,000 light years from end to end. But the disk does not remain perfectly flat. In some areas it warps slightly upward or downward, forming subtle bends. These warps are usually caused by interactions with dwarf galaxies or by uneven flows of gas from the halo. Even tiny gravitational influences, tiny compared to the mass of Andromeda, can create visible waves in the disk over millions of years. These ripples move slowly through the galaxy, changing its shape in ways that reveal its sensitivity to its environment. If we could view the galaxy edge-on, the disk would appear as a thin, bright line with a thicker bulge in the middle. This thin shape is striking because it shows how precisely balanced the galaxy is. Gravity, rotation, and mass distribution all work together to maintain this flat structure across enormous distances. The thinness of the disk is another measure of Andromeda's scale. Maintaining such a structure requires a perfectly coordinated rotation across hundreds of billions of stars spread over vast regions of space. Every part of the central region and disk highlights how massive and stable Andromeda is. The black hole anchors the core. The bulge provides gravity for the inner disk. The spiral arms guide star formation. The disk rotates with incredible precision. The entire structure holds together because of the dark matter halo surrounding it. Together, these features show that Andromeda is not just large in appearance, It is internally complex, balanced, and shaped by billions of years of evolution. The deeper we look into Andromeda's center, the more we realize how much energy flows through it, even when it appears calm from a distance. The stars near the core orbit so quickly that their combined motion generates tremendous heat and turbulence. This constant motion stirs the region like a cosmic whirlpool. Even though the black hole itself is quiet most of the time, the crowded environment around it never rests. Gas clouds fall inward, collide, and get torn apart. Stellar winds from aging stars push material outward. Supernova explosions create shockwaves that echo through the central bulge. All of these processes happen within a region that, compared to the galaxy as a whole, is incredibly small. Yet their influence shapes structures that extend far into the disk. When we pull back from the core and look at the inner disk, its scale becomes even more striking. The disk contains so many stars that even a small patch of it may hold millions. The stars move in orderly paths, following the rotation of the galaxy. But beneath this order lies a delicate balance. The rotation must be fast enough to support the disk, yet not so fast that the stars drift apart. This balance is maintained by the dark matter halo. Without that invisible mass, the disk would collapse or disperse. The halo gives the disk strength, allowing it to hold its shape for billions of years. The inner disk also contains subtle waves of motion. These waves are created when the gravity of a passing dwarf galaxy tugs on Andromeda's disk. The pull may be tiny, but the disk responds like a sheet of water disturbed by a stone. Waves ripple outward slowly, bending the disk in small but noticeable ways. These waves take millions of years to move through the galaxy. By the time they fade, new waves may form from other interactions. This delicate, constant motion shows how sensitive Andromeda is to its environment. Even small galaxies can shape its structure if they pass close enough. As we move farther outward, the spiral arms become the dominant feature. Their scale is enormous. Each arm stretches for tens of thousands of light years and contains countless young stars. These stars shine brightly, giving the arms their striking blue appearance. Gas clouds weave through the arms, forming thick lanes of dust and hydrogen. These clouds are some of the largest structures in the galaxy. They can span hundreds of light years and contain enough material to create thousands of stars. The arms also contain cavities where stars recently exploded as supernovae, carving out bubbles in the surrounding gas. Despite their appearance, the spiral arms are not permanent structures. They shift slowly over time as density waves move through the disk. Stars drift in and out of the arms, spending only a fraction of their lives inside these bright regions. But the pattern of the arms remains, held together by gravity and the overall rotation of the galaxy. This dynamic nature shows that even Andromeda's most recognizable features are constantly changing, shaped by the ongoing movement of stars and gas. Beyond the arms, the outer disk contains a more diffuse population of older stars. These stars are widely spaced and move with slower rotation speeds. Their presence shows how far the disk extends. Even though these stars contribute little to the galaxy's overall brightness, they reveal the true width of the disk. Many of them follow orbits that are slightly tilted or warped, reflecting disturbances from past interactions. Some have migrated outward over billions of years, carried by subtle changes in the disk's gravitational structure. The outer disk also contains regions where the gas becomes extremely thin. Star formation is rare in these areas because the gas is not dense enough to collapse. These outer regions reveal the limits of the disk's ability to grow. Beyond a certain point, the galaxy's gravity is too weak to hold thick layers of gas, so the disk slowly fades into the halo. But even here, faint traces of structure remain. Some stars follow gently curved paths that trace the edges of the spiral pattern. Others drift in nearly circular orbits, shaped by the extended dark matter halo. These faint boundary regions show how smoothly Andromeda transitions from its bright inner regions to the vast halo surrounding it. If you were floating far above Andromeda and looking down, the core would shine as a bright, compact sphere. Surrounding it would be the glowing bulge, fading gradually into the spiral disk. The arms would sweep outward in graceful arcs, speckled with bright clusters and dark lanes. Beyond the arms, the disk would become faint, blending slowly into the halo. This view would reveal the full structure of the galaxy, from its dense center to its sparse outer edges. It would show how each layer connects to the next, forming a single, enormous system stretching more than 200,000 light-years across. But even this dramatic view would not capture Andromeda's true scale. To see that, you would need to zoom out even farther. As you pull away, the halo would become visible as a vast cloud of stars surrounding the disk. This halo would appear far larger than the bright galaxy at its center. Streams of stars would stretch through it like faint trails. Globular clusters would hang like tiny lanterns. The halo would extend in all directions, forming a sphere so enormous that the visible disk would look like a small glowing dot at the center. This view reveals the true size of Andromeda's gravitational influence, far beyond the light we can see. The more we examine Andromeda's central region and disk, the more we understand how all its layers work together. The core anchors the bulge shapes the inner disk. The inner disk supports the spiral arms. The arms guide star formation. The outer disk transitions into the halo. The halo extends the galaxy's reach across hundreds of thousands of light-years. Each part forms a link in a chain that stretches from the black hole at the center to the most distant globular clusters on the edge of the halo. And this layered structure is what gives Andromeda its incredible power. It is not simply large, it is organized, balanced, and shaped by billions of years of evolution. Its true scale cannot be seen at once. It must be traced through its stars, its gas, its dust, its motions, its mergers, and its dark matter. Only then does the full picture appear, a galaxy that dominates its region of space and extends far beyond the faint glow visible from Earth. The true scale of Andromeda becomes even more extraordinary when we look at its future. Everything we see in the galaxy today, the stellar streams, the halo, the disk, the spiral arms, the bulge, the black hole, exists at one specific moment in time. But galaxies are not static. They evolve over billions of years, changing shape as gravity reshapes their stars and gas. Andromeda is no exception. In fact, its future represents one of the largest and most dramatic events our galaxy will ever experience. The collision between the Milky Way and Andromeda is not just a distant possibility, it is an unavoidable consequence of their motion across the local group. This future encounter reveals Andromeda's full significance, not only as a large galaxy, but as the dominant force shaping our region of the universe. Right now, Andromeda is moving toward the Milky Way at about 110 kilometers per second. This speed is astonishing when you consider the distance between the galaxies. Space is not empty air, it is a vacuum where motion continues indefinitely unless acted upon by another force. Andromeda's motion toward us has been happening for billions of years. Even though it will take billions more for the galaxies to meet. The journey is already well underway. Their halos are beginning to overlap. Their gravitational fields already interact. Tiny motions inside both galaxies, warped disks, stretched streams, shifting orbits are early signs of the encounter that lies ahead. When Andromeda and the Milky Way finally meet, the first contact will not be a collision of stars. The space between stars is too vast for that. Instead, their halos will collide first. These halos contain dark matter, gas, and stars scattered across hundreds of thousands of light years. As the halos begin to merge, they will create tidal forces that ripple through both galaxies. These forces will distort the disks, stretching them into long, thin shapes. Some stars will shift into higher orbits. Others will fall inward. The spiral patterns will warp, creating chaotic structures that resemble cosmic whirlpools. This phase will last millions of years, with each galaxy passing through the other before separating again. The second encounter will be even more dramatic. By this point, the galaxies will have lost energy through gravitational interactions. They will slow down slightly, making the second pass closer and more disruptive. Their disks may twist into elongated shapes. Huge waves of gas will ripple outward. Star formation may spike as gas clouds collide and compress. Bright clusters will flare into existence. Entire regions of both galaxies will take on new shapes, forming bridges of stars that stretch between them. These bridges will act like cosmic ropes, pulling the galaxies even closer. Eventually, after several passes, the galaxies will no longer separate. They will fall together, merging into one enormous structure. The final merger will look nothing like the spirals we see today. The new galaxy will be larger, rounder, and far more massive. Some astronomers predict it will resemble a giant elliptical galaxy. Others think the merger may produce a unique hybrid structure. Whatever shape it takes, the new galaxy will contain the combined stars, gas, and dark matter of both the Milky Way and Andromeda. It will dominate the local group completely. The stars inside each galaxy will experience the merger as a slow transformation of their environment. Over millions of years, their orbits will stretch, twist, and reshape. Some stars may be thrown into the outer halo of the new galaxy. Others may fall toward the center, creating bursts of star formation as gas follows them inward. Some stars will be ejected entirely, becoming intergalactic travelers drifting through the void. Despite these dramatic changes, the probability of stars physically hitting each other remains extremely low. The distance between stars is too great. The galaxies will pass through each other like clouds of glowing sand. At the center of the merged galaxy, the two supermassive black holes, one from the Milky Way and one from Andromeda, will spiral together. As they draw closer, they will release enormous amounts of energy in the form of gravitational waves. These waves will ripple through space, carrying away energy and pulling the black holes even closer. Eventually, the two will merge into a single black hole, millions of times more massive than the Sun. This new black hole will become the anchor of the merged galaxy, shaping the orbits of nearby stars and stabilizing the core. After the merger, the new galaxy will continue to evolve. Star formation may continue for billions of years if enough gas remains. The halo will grow as new stars drift outward. The structure will slowly take on a smoother, rounder appearance. Over time, the galaxy may absorb smaller companions, adding new layers to its halo. The local group will become more organized around this single massive system. The merger will be one of the defining events in the region's cosmic history. What makes this future so important for understanding Andromeda's scale is that it shows how massive and influential the galaxy must be to reshape the entire local group. A smaller galaxy would not produce such dramatic changes. A weaker galaxy would not pull the Milky Way toward it. Andromeda's gravitational power extends across millions of light years, altering the motion of dwarf galaxies, shaping the halo of the Milky Way, and determining the long-term future of our region of space. Its scale is not just physical, it is dynamic. Its motion and mass are powerful enough to change the structure of the universe around it. This future collision also reveals another important truth. Galaxies do not live forever in their current form. They merge, evolve, and transform into new structures. The galaxy we see today as Andromeda will not exist in the distant future. It will become part of something much larger. The faint blur we see in the night sky is not just a neighbouring galaxy, it is a vast cosmic engine moving toward us, shaping our destiny on a timescale far longer than human history. As we explore Andromeda's future even further, the scale of the coming transformation becomes clearer. The merger with the Milky Way will not be a single moment, but a drawn-out reshaping of both galaxies. On a human timescale, nothing will appear to happen. The sky will look the same for tens of thousands of years. But over millions and billions of years, the changes will be enormous. The stars in both galaxies will shift into new orbits. Gas clouds will be pulled into new patterns. The smooth spiral shapes that define the Milky Way and Andromeda today will gradually dissolve and reform. The galaxies will stretch, twist, and fold into each other like two vast tides colliding in slow motion. From inside the Milky Way, the view of Andromeda will become increasingly dramatic. Today, it appears as a faint blur. In a few billion years, it will grow brighter, larger, and more detailed. The spiral arms will become visible to the naked eye. The core will shine like a distant lantern. As the galaxies draw closer, Andromeda will dominate the night sky. It will appear so large that it will take up a significant portion of the heavens. Stars within Andromeda will appear as individual points of light. It will be one of the most awe-inspiring sights the universe can offer, though no humans will likely be around to witness it. Nonetheless, imagining this future offers a glimpse into the enormous scale of the event. Once the merger is underway, the shapes of both galaxies will become chaotic. Their disks will warp into long glowing arcs. Bridges of stars will stretch between them. Some regions will collapse inward, forming dense knots where star formation bursts to life. Other regions will stretch outward into long tidal tails. These tails will carry stars far from their original homes, scattering them across vast distances. Some of these stars will drift into intergalactic space, permanently leaving the new galaxy behind. Others will settle into extended orbits around the merged system, becoming part of a new, much larger halo. These tidal tails and bridges show how galaxies communicate through gravity. Even though stars rarely collide, the collective pull of billions of stars reshapes the structure of both galaxies. Gravity stretches material across tens of thousands of light years, creating patterns that reveal the deeper forces at work. These patterns are temporary, lasting only a few 100 million years. But during that time, they create some of the most striking shapes in the universe. The merger will be messy, beautiful, and vast beyond anything we can easily imagine. Eventually, the chaos will settle. The gas in both galaxies will fall inward, forming new stars in powerful bursts of activity, these new stars will shine brightly, creating clusters that glow for millions of years before fading. Meanwhile, the combined rotation of the galaxies will slow as energy is distributed throughout the new system. The spiral arms will fade, the disk will thicken, the bright, clean spiral shape will be gone. In its place will be a giant, smooth-rounded galaxy, a new system often referred to as Milkdromeda. This new galaxy will contain far more stars than either the Milky Way or Andromeda alone. It will have a far larger halo. It will dominate the local group in a way no single galaxy does today. At the centre of this new galaxy, the two supermassive black holes will spiral together. Their merger will be one of the most powerful events in the universe. As they close the final distance between them, they will release intense gravitational waves that ripple through space-time. Although these waves will be imperceptible to any life inside the galaxy, they will show up clearly to distant observers with the right instruments. The merged black hole will be enormous, anchoring the new galaxy and shaping the motion of stars around it for billions of years. Over longer timescales, the new galaxy will continue to grow. It may absorb the remaining dwarf galaxies in the local group. It may continue interacting with nearby systems. Its halo will expand as stars drift outward into long looping orbits. The structure of the galaxy will become smoother and more stable. The bright bursts of star formation will fade as gas is used up. Eventually, the galaxy will enter a quieter stage, glowing softly with the combined light of trillions of stars, each one following a path determined by billions of years of mergers and evolution. This entire future, from the first signs of gravitational interaction to the final quiet elliptical galaxy, highlights the enormous influence of Andromeda. A galaxy must be massive to reshape the Milky Way so completely. It must be enormous to pull the entire local group into a single structure. The fact that Andromeda plays such a large role in this cosmic transformation shows how impressive its true scale is. It is not just a nearby spiral, it is a major gravitational force in the universe, capable of altering the fate of our galaxy and rewriting the structure of our cosmic neighbourhood. When we step back and consider everything, from its vast halo to its luminous disk, from its tidal streams to its scattered clusters, from its future merger to its ancient collisions, we see a galaxy that is far larger than its appearance in the night sky suggests. The faint blur hiding in the darkness is a titan. It spans hundreds of thousands of light years. It holds 1 trillion stars. It contains ancient fossils of galaxies long destroyed. It commands the motion of dozens of smaller companions. It influences the Milky Way. It defines the structure of the local group, and it will shape the future of our region of the universe. The true scale of Andromeda is not a number. It is a story written across billions of years and hundreds of thousands of light years. A story of growth, of collision, of gravity, of evolution. A story far bigger than anything we can fully grasp. And yet, from Earth, we see only a dim patch of light, a reminder that the universe hides its giants in plain sight. Andromeda looks small from Earth, but its true scale is far beyond anything we can grasp at a glance. It is a galaxy shaped by ancient collisions, held together by invisible matter, wrapped in streams of stars, and powerful enough to reshape the Milky Way itself. Everything we see in the night sky is only the surface of a structure that stretches across hundreds of thousands of light years and reaches deep into the future of our universe. The faint blur overhead is not just a neighbour, it is a reminder of how huge the cosmos really is, and how much more there is still to understand.